Please welcome Senior Vice President and Director of IBM Research, Darío Gil.
Thank you. Thank you, and good morning, and welcome to the IBM Quantum Summit. You're all looking great. It's great to have all of you here in New York. We haven't been able to be together since 2019, and you're in for a treat today, right? We're going to share so many fascinating advancements that are happening in the world of quantum computing, and we're going to have an opportunity to have a great dialogue. I have the enormous privilege of being the director of IBM Research. And as the director of research, what gives me, an enormous joy every day is to be able to work in a community of scientists and engineers and designers of every possible background. We have mathematicians and electrical engineers and computer scientists and physicists and mathematicians of every kind. And what brings us together, what binds us together as a community, is this passion that we have to imagine the new possibilities with which we do information technology and computation. It is about combining different disciplines to push the field of computing forward. We say that our mission is to create what is next in computing. And simply put, we're living in a moment where computing, with a capital C, as I like to call it, is going through one of the most exciting moments since the advent of digital computers in the 1940s. And what we are witnessing is going to be the convergence of a set of technologies and methodologies. I like to summarize it as bits plus neurons plus qubits coming together in an environment of a hybrid cloud computing fabric. And this convergence and the advances that we are going to be sharing with you today in the world of quantum is going to have such profound implications to our businesses, to government, to our society. And being able to live in this moment where we get to see the frontiers of all of these technologies is something that I think we should all celebrate and enjoy, basically, every minute of the day that we get a chance to push these areas forward. So I want to set the context before we get into quantum computing, because this is going to be a layer of computing that builds on the incredible technologies that we already have. The first thing that we all recognize is that we already have an enormously rich computational environment around us. We have the world of public cloud. We have our private environments. We have edge environments. And one characteristic that we see is that it's very heterogeneous in nature. There's a lot of diversity of compute infrastructure, and there's a lot of diversity also of delivery models. Now, with that diversity comes complexity, and the reality of it is that in this hybrid cloud environment, we often have to wrangle and deal with how do we orchestrate all of these workloads in this heterogeneous environment. So one core focus that we also have as a company and what is happening in the world of hybrid cloud is to simplify this diversity, the multiplicity of control planes that exist in these different computing environments through two core philosophies. One is open technologies. And here what we are showcasing is Red Hat Open Hybrid Cloud Platform, OpenShift, as a means to be able to orchestrate this complexity. And the second element of it is abstractions. Being able to have a more unified control plane built on open technologies that allows us to then tap into the power of this distributed and heterogeneous environment as if it felt like a single computer. So the vision that we have forward on orchestrating this capability is to be able to deliver more choices as more providers and the full ecosystem that provides cloud-native services of all scales become available to us, to allow in our developer environments less time to develop and to bring costs down through choice by 60%. So this vision is a vision of frictionless multi-cloud computing. It's the idea of treating the cloud and the heterogeneous environment as if it felt like it was a single computer. The second macro trend that we're also witnessing that builds this foundation of technology in computing is, of course, the world of AI. And in the world of AI, what we've also witnessed from an infrastructure and a software development environment is the power of specialized compute architectures, like accelerators and GPUs. But we've also witnessed that we've had to deal with also a lot of fragmentation. Everything from having your GPU under your desk to be able to do models, to small local clusters, to environments that you have on different public clouds. But the reality is like wrangling with all of these choices and the whole stack has been complex. So similarly to what I was describing in the world of hybrid cloud, we have a tremendous focus to create a more unified full stack environment, again, built on open technologies and abstractions to enable cloud-native AI-centric supercomputing. And what you're seeing here by combining these areas, and in the future, by the way, we're also making significant investments to create the next generation of accelerators that are native to the neural network workloads that, that are the heart of AI, sort of beyond the GPU approach. When you combine this with the massive changes that we're seeing in AI on the topic of self-supervision on large parameter models or foundation models, what we are also seeing is that you can increase the methodology and the productivity which you can develop AI pipelines and create derivative models from those foundation models by a factor of 10x. And we've seen this recently as an example in the way we have delivered Project Wisdom, that you can look it up, to assist the developer in Red Hat, in Ansible environments, to be able to program and assist with the programming environment as you are doing IT automation. So in this context, the base in which we're going to add now the layer of quantum computing starts with the realization that bits and neurons in this hybrid cloud is allowing us to create this cloud-native AI-centric supercomputing. Which brings us to the heart of today. The third element of that equation is going to be enormously profound. And this is the world of quantum-centric supercomputing that is going to add to these layers. And in this vision, we are going to have both classical and quantum resources that need to be integrated and orchestrated. The classical resources will involve everything from the orchestration of workflows to a quantum serverless environment in which we're going to abstract the complexity of this infrastructure to the user and to the developer so that they don't have to deal with all of these issues, and the ability to create nested programs and also program optimization, including circuit knitting, which we will have a chance to discuss today. Now, that environment is going to allow us to tap into not only single computational nodes, where again there is classical and quantum orchestration that needs to happen, enabled by Qiskit runtime as a service, but also importantly to the fact that we have a distributed quantum network where we have multiple computational quantum nodes that also we can tap into. And we're going to see how this vision is going to come a reality with a number of exciting announcements. So in this vision, just like we were talking about bits and neurons coming together in AI-centric supercomputing, we are going to bring bits and qubits together in quantum-centric supercomputing. So what are some of the major accomplishments that we are going to get a chance to go into a lot of detail today in making this a reality? The advancements focus on three core dimensions of how to increase performance of our quantum systems, the value that these systems provide, and the adoption, the community that is taking advantage of these areas and growing quantum. So on performance, the dimensions in which progress is measured is the scale of the processors and the systems that we can create, the quality, how well they obey quantum mechanics, and the speed of these systems. And we measure them through the number of qubits that we have, the quantum volume of the systems, and CLOPS, the circuit layer operations per second. How fast do they run? So these are the three core dimensions. And on qubits, we are, as you know from our roadmap, we are extremely proud to be able to share, and you'll see more details a little bit later, Osprey, a 433-qubit processor, by far the largest processor ever created in the world of superconducting qubits, and is this continuation of the evolution of a family of processors that we name after birds, that we went from, by the way, last year when we announced Eagle with 127, it was the first time anybody had built and crossed the 100-qubit barrier. So now with Osprey, we've increased that tremendously, and it brings all of the technologies that we've been building over the years, including 3D integration, multi-layer wiring, being able to separate the qubit control plane from the connectivity and the readout planes. So it's a really amazing tour de force in terms of materials, devices, packaging, and on the quantum processor itself. And you're going to get to see a lot of it, of what happens and why it makes it so special. But I just could not be more proud of the accomplishments of the team in making this happen. So just to put in perspective how much progress is occurring, since the last Quantum Summit, in just a year, we have improved the number of qubits that we can create in a processor by 3x. Quantum volume has increased by 4x. And CLOPS has increased by over 10x. It is an undeniable amount of technical progress that is occurring, and the rate and pace is only accelerating. Now, in the context, once you have better technology, how can you also improve the entire system and software stack to be able to deliver more value? And one of the areas that is extremely important for this software stack and value creation is the evolution from static circuits to dynamic circuits. Simply put, a static circuit is like a sequence of gates where you run them in sequence, and in the end, you perform a measurement. And a dynamic circuit is one where you actually have intermediate measurements in the execution of the circuit, such that you can make conditional changes on the upcoming gate execution as a function of that intermediate measurement. And what this allows us to do is to have more efficient circuits. Simply put, the power is to do more with less. We have limited amount of time with which to execute our circuit, driven by coherence, and with dynamic circuits, we can greatly improve what the quality of those circuits are and what we can achieve within the window of the coherence time that we have. So this is going to be something that is now available in the latest IBM Quantum systems. And in Q1, we will also incorporate it in our Qiskit runtime environment. So again, this is another area where there was a lot of work. It was a key element of our roadmap to make it happen, and the team has been able to deliver. And on the area of adoption, Qiskit continues to be the leading quantum developer platform. And this is a heart of our commitment to have an open environment and a collaborative environment where we can benefit from the collective advances and wisdom of the entire community. To give you a sense, within the scientific community, quantum machines, of course, have become a fantastic scientific instrument with which to advance research. Here's the number of publications and how they have grown using IBM Quantum systems. Close to 2,000 now scientific publications that have been generating using our systems. You also see the fantastic growth on Qiskit downloads, close to 1.8 million now. And this is one of the areas that we care so deeply about, that we continue to provide, and all of us create value together in creating this environment. And within the context of institutions now, of exploring the implications of quantum, and from use cases to doing joint R&D, and a variety of applications. Now the family in IBM Quantum Network is over 200 institutions are part of it. You're seeing from leading Fortune 500 and 100 companies to startups that are also pioneering this wonderful industry that we're creating together, to universities, to national laboratories around the world. It's a fantastic community that keeps growing. And we could not be more proud. I know many of you represent also institutions and, and startups that are part of this network, and we're so thankful that you choose to collaborate and partner with us. So performance, value, and adoption are undeniable elements of waves of progress. So you can feel this swell of progress of what is happening in our industry. It's literally, viscerally, you can sense how the technology is advances, how the interest is advancing, and how the community is growing. Now, as far as we have come, and we shared almost exactly 2 years ago, right, the first development roadmap, where you saw the progress in terms of system modularity, in terms of number and quality of the quantum processors, but we also shared the software stack, from kernel developers to algorithm developers to model developers. And as far as we have come we've also reached the conclusion that for the next wave of the roadmap, we needed to think even more ambitiously, and that we needed to go back to the drawing board and imagine the next generation of technology, of systems, and quantum. And that is something that we're also very proud now to be able to share with you. Because to enable this to happen, we need a new system. And a new system that is designed with modularity at the heart of it all. Because to create systems that are going to have tens of thousands of qubits, that are going to need to orchestrate classical and quantum resources in a new way, we needed to expand the range of possibilities. And that is IBM Quantum System 2. And what you're seeing here is how we're going to bring it to life. We will have a much larger system of refrigeration in there, such that we can fit within a single cryostat systems now that will have even thousands of qubits within one. But importantly, the modularity is designed throughout. Not only inside how we are going to bring together different quantum processors, but importantly, the fact that multiple systems are going to be able to be connected to one another. So in these configurations of 2 and 3 systems, and in the future even expanding them further within the context of a quantum-centric supercomputer, where we will see connections that range from classical connectivity to quantum mechanical connectivity in terms of communications. So one of the things that the team is creating and designing is the convergence of communications and computing in the field of quantum. This is an enormously ambitious idea of how we're going to bring classical and quantum information with modularity, with very large systems where communication and quantum computing are coming together. So with IBM Quantum System 2, we're already building and designing it. And our objective is to be able to instantiate and deliver that first system 1 year from now, what you're seeing in here. So you've seen the progress that we're seeing in the technology on the full stack. You're seeing how we're going to bring together, through modularity, a much larger system that is going to bring us to that era of quantum advantage. So I want to close by asking of ourselves the progress that we're seeing in the field and how and whether quantum computing is now an industry. And I would argue that the progress that we're seeing is undeniable, and the answer is yes. If you look from a venture capital perspective, and we have a wonderful collection of startups in here, the growth of investments that is happening in both software and hardware companies. And on top of that, of course, we would have to add the investments that major technology companies like IBM are making in the field as well. The progress is undeniable in terms of the level of interest, the investment, and the talent that is coming into the field. You're seeing it in the development of intellectual property and patents in this space and how it is growing. Again, the progress is undeniable. This is all fed by advances in the scientific community, right, of continuously to think through and create new ideas and push the limits forward. And you're seeing this also in the growth of publications related to quantum computing. Across all of these spaces, we are seeing and we are a proud member of that industry and to push the frontiers of the quantum industry. For IBM Quantum, our mission is twofold. It is to bring useful quantum computing to the world, and today is going to be a wonderful expression of the progress we're making on that front. And second, to make the world quantum safe. We all know also the implications that quantum computing will have and the evolution towards quantum-safe cryptographic protocols is going to be also a central element of our effort, of our talent, and of our community development. That is the dual mission of IBM Quantum. And at the heart of all of this is a community. It's a community through Qiskit, and it's a community through our university and partner network that we have. And this is the area where you get the sense that there is indeed this swell of progress. When you see the energy and the enthusiasm that we all get to witness in the world of quantum, how much appetite there is to learn, to contribute, to shift careers into this new area, you know that we are together onto something really big. And this is just the beginning of that momentum. And as more and more talent comes into the field, the rate of progress is only going to accelerate. So I close by sharing with you what I really believe in my heart, and that is that the future of quantum is all of us who are here and this extended community, and that we have an incredibly bright future, and you're going to get a chance now to be wowed by the depth of progress and the sheer amount of things that we're going to be announcing today.